Well, hello there and welcome to my video on resistors, parallel and series. This is the theory section, so if you would like to see examples, please check out my next videos which will come after this one. So let's get going. Okay, so we're looking at parallel and series resistors. Let's look at series resistors first. So series resistors is two or more resistors sharing or connected to one node on one of their sides each. So what does that mean? It means they share the same current, and let's have a look at that. So they are connected to the same node in the middle. As said, they're sharing one node, and the current through them is exactly the same. This same current flows through that resistor as flows through that resistor, which means we have voltage division because the voltage over there will be different to there as the resistances are different. If we look at V equals IR, we have R1 here and we have R2 here. So if we keep current the same, because we can see it's the same, then if resistance varies from this one to this one, the voltage has to vary from this one to this one to obey Ohm's law. Okay, so from KVL we can say minus VI plus V1 plus V2 is equal to 0. And if we take the VI over, then VI is equal to V1 plus V2. And we can draw an equivalent circuit for these resistances. Your R equivalent will be R1 plus R2, and if you have more than two resistors, it will be all the way from R1, R2, R3, R4, all the way up to Rn equivalent resistance, and we can redraw that as one resistor, as per the resistance videos before this one. And the current will of course still be the same current that was there before. Okay, so now we want to look at the voltage over R1 and R2. We want to say, okay, sorry, let me move that. We want to say, okay, well, how can we calculate the voltage over only R1 or over only R2 if we're given VI and say R1 and R2? So if we're given VI and R1 and R2 only, then we want to say what is the voltage of R1 and what's the voltage of R2. So from KVL, we know that VI equals V1 plus V2. We know what V1 is. It's I1 R1 or IR1, and V2 is IR2. We can then take out the I, which is common, and we can then say, well, we can solve for I by saying VI divided by that. We can divide by R1 plus R2 on both sides. Then I is equal to VI over R1 plus R2. Now I can say, well, we want the voltage over R1 and R2 separately. So we know V1 is equal to I times R1. Well, we can sub I into there. From there, we sub it in there. Then V1 is equal to this. So now we know what V1 is in terms of VI and both resistances. Okay, we can do the same thing for R2. V2 is equal to IR2. We know what I is because we just solved for it, VI over R1 plus R2. So we can sub in for I over there, over here. And then we can move the VI out and get R2 over R1 plus R2. Just something to take note of is the fact that the value of the R value and the V value is the same on the top. So V1 and R1 have the same subscript, whereas here the same thing, V2, R2. Okay, so that is for voltage. Also, for N series resistors, for number N series resistors, so N number of resistors in series, Vn is equal to Rn, note the same subscript, over R1 plus R2 plus R3 all the way up to Rn times Vi. Now we look at parallel resistors. So parallel resistors, what's a parallel resistor? There are two or more resistors where both ends of each resistor are connected to the same node. So what do I mean by this? Well, it means they have the same voltage because the current that flows out of here is divided into this node and this node, depending on what the resistance is. More resistance, less current. Less current, more resistance. From Ohm's law. So if you increase the current, you're going to have less resistance. If you have more resistance, you're going to have less current. And that makes logical sense because the more resistance you have, the less current you'll have. But that also means that the voltage is the same, and that's because the nodes are connected on the one side with the voltage inputs, into the resistors, and it's also connected where the output of the resistors connect. So the voltage is exactly the same. And what does this imply? This implies current division. So what can we say from current division? Well, we can apply KCL at the top node, which is the sum of all the currents in the node being equal to 0. So that means that I is equal to I1 plus I2. All I've done is I've said I as the input current is positive, minus I1 minus I2 because they're outputting equal to 0, and then took the I1 and I2 over. Okay, if you don't understand it, please check out my video on KCL. We also know that VI is equal to I1 R1 and I2 R2 from there and from there. So what can we do with this? Well, we can say this I1 divide by R1 on the side of VI, so VI over R1 will be equal to I1, and VI divided by I2 will be equal to R2. Then we can say, well, we have a formula for I1 and I2, so we can sub into this formula. So we can say I1 subbed in there is VI over R1 plus VI over R2 for I2. And that is equal to this if you take out the VI. And this is what is known as R equivalent, the equivalent resistances across the circuit. And we draw it like that. Okay, so what can we say now? Well, I'm going to take this away. We can say we have VI over R equivalent. So we know this is the equivalent resistance. 1 over R equivalent is equal to this. So 1 over R equivalent is equal to this. And if we invert that, then we get this. And we also get an LCD to make it simpler. So R1, R2 will be your LCD, your lowest common denominator. And then you have to add R2 and R1 on top to make up for the common denominator. And then this is to the minus 1 because I flipped it from there to there. Then R equivalent, if you flip this, equal to R1, R2 over R1 plus R2. So now we know this. We want to know, just like we wanted to know what the voltage there is and the voltage there is, we also want to know what the current there is and the current there is, the separate currents, because the current divides between the two resistors. So now what can we say? Well, we can say VI is equal to I times R equivalent, if we draw our equivalent circuit. But we know what R equivalent is, we just worked it out. That is the entire purpose of working on R equivalent, by the way. So now we can sub that into the place of R equivalent. But we also know that VI equals IR1, and that is also equal to I2R2. From there and from there. So I1R1, I2R2. Then we can say, well, we have VI over here, so why don't we sub this into there for VI? Then we can say VI, which is this, is equal to I1R1, and VI, which is this, is equal to I2R2. Then we can say, well, we have R1 and R1 over here, so we can cancel them away, or divide both sides by R1 if you prefer to see it like that, and the same with R2 in this one. Then we solved for I1 and I2 successfully, and it's just in terms of I, the input current, and the resistances. So if we're given only the current and the resistances, then we can work out the individual currents.